So let's move on to model evaluation. Till this point of time, we have learned how to develop machine learning algorithms in Python. We have essentially missed out one point. How do we evaluate them? How do we understand what is the performance of a particular model, or how does one model perform in comparison with another model? Now, generally, let's say for a normal use case, let's say you give a test, and in that test, the outcome is a percentage of score. Let's say you score around 85% of marks for a test that you have given recently. Now, percentage of score, this is a metric that you have used to understand how you perform in that particular examination. That's how you evaluate yourself. Similarly, when you consider a machine learning use case or a machine learning algorithm, you would need similar metrics that will help you understand how do machine learning algorithms perform. Now, these metrics will be different for a linear regression use case or a classification use case. Let's handle these topics one by one. Let's start by understanding how can we evaluate machine learning algorithms that are regression models. Now, as you already know, regression models have the target variable, which is continuous in nature. So you have a numeric target variable. Now, one of the most important and most popular metric that is used to evaluate a regression model is the coefficient of determination, also popularly called as R squared. Now, R squared could be a number which is standardized and will help you understand in layman terms how does a model perform. It could be a value, let's say like 0.04 or 0.4 or 0.99. Now, this can roughly be translated to a percentage. So let's say for a model, for a linear regression model, you have the R squared value as 0.95. You can roughly translate this as around 95% of the variance is explained by the model. Now, the higher the value is, the better the model is. And R squared can be calculated using the simple formula 1 minus the summation of square of the differences between the actual and the predicted divided by the summation of square of the difference between the actual and the mean. Similar to coefficient of determination, you will have a couple of other metrics. There are several others, and in this slide I've just enlisted a few of them. You have another metric like mean squared error. Mean squared error, in this scenario, you would actually take the summation of the difference, the square of the difference between the actual and the predicted divided by the number of samples. Now, this is not a standardized value. Let's say for a model, you will have mean square error as 500, and for another model as the mean square error is 600. So the thumb rule is the lower the value is, the better the model is. The reason we use square in any scenario would be to amplify the effect of larger error. So let's say if the error was 2, you take square of 2 as 4. So 4 would be used to contribute to the overall error measure. But then let's say the error was 10, the square of that would be 100. So you have a larger impact on the total overall error measure. So mean squared error is actually a very important metric that is used in conjunction with R squared, where you're trying to understand how good your model is. You generally want a model that is having lower mean squared error. Similar to mean squared error, there are a couple of other ones. MAP, that is MAP, mean absolute percentage error. Pretty much from the name itself, we can kind of understand what would this account to. So you're saying the percentage error, the absolute percentage of the absolute error, and then you're taking a mean of that. So it's nothing but the difference between the actual and the predicted, the absolute difference between the actual and the predicted, divided by the sum of divided by the actual value into 100. So you're getting a percentage based error. So let's say you have a value like 0.15, which means 15% of error. Now you can use this number 15% directly on the scale of y. So let's say your y, that is your target variable, has values generally between 500 to 1000, and you're saying that on approximately 15% is the error that you face while you work on predictions. So you can kind of understand what kind of error you will get when you're trying to predict on an average. So it's a great tool to understand error in a layman way, but then not as useful as mean square error, because over here in this scenario, you would use a higher penalty on higher error, but that is not the case with MAPE. But then there are different use cases where you'll have a specific requirement to leverage MAPE, or you would have a specific requirement to mean squared error. And as similar on similar lines of mean squared error, we also have root mean squared error, like just the root of the mean squared error. Apart from this, there are a couple of other statistical measures or other metrics used to understand model performance for regression models. So it could be something like mean squared log error and many more variations. So in cases when you want differences between smaller numbers to be treated as a smaller impact, larger numbers to be treated as a larger impact, you have different scenarios. So based on your scenario, what you are looking forward to, you would actually choose one metric that would be important for you to understand how your model is performing. So let's take a look at how we can calculate these metrics for a regression use case in Python.